Water is the great enemy to Florida's roads and highways. Although nothing can totally resist the effects of water, one base material holds up better than most. Soil cement is the low-cost, durable material that also provides extraordinary support and strength that increases with age. Soil cement is an intimate mixture of Portland cement, water, selective soil and/or aggregates compacted to a high density that becomes a hard, durable paving base material as the cement hydrates over time. A surface course is usually placed on the soil cement base to complete the pavement. The opportunities and applications of soil cement vary as widely as the combination of conditions found on every roadway construction site. However, there are only two fundamental ways of preparing soil cement: central plant and mixed in place. With the central plant method, the base material is prepared at a plant, usually off the construction site. It is then hauled to the site in dump trucks and processed and compacted with conventional equipment. With this method, no special processing equipment is required of the contractor. With the mixed-in-place method, the cement is added to the material already present in the roadbed. The materials are then mixed in place into a uniform soil cement product. After mixing, the soil cement is shaped and compacted with conventional equipment. One of the wonderfully economical qualities of soil cement is that the mixture can be of a wide variety of materials: lime rock, shell, clay, or sand. It can also be waste materials. Screenings from rock crushing operations and crushed concrete also work well, as does crushed flexible paving material that has lost its resilience. The ability to use just about any kind of material accounts for the low cost of soil cement, not only as a base material, but also for slope protection and stabilization, and impermeable liners for ponds and waste disposal sites. The most favorable materials in Florida are combinations of sand, lime rock, shell, and clay. With proper gradation, these materials require the least amount of cement content, about 5% by weight. Low construction cost represents only one of the many advantages of soil cement in road paving. Low maintenance costs are also significant. Rather than deteriorating, soil cement increases in strength over time. As the cement continues to hydrate, it becomes even more durable, affording continuing performance over time. Tests of highway material continue to find roadways showing more than 4 times the 7-day compressive strength after 18 years of use. Also, because of soil cement's strength and stability in the presence of water, it resists the erosion and deteriorating effects realized by other base materials. Speed of construction is another advantage when utilizing soil cement bases. Out of necessity, all operations involving construction of the base are usually accomplished in one day. After the soil cement has been compacted and finished, Florida's frequent rains will not cause it to soften, rut, or otherwise deteriorate. Rather, the rain augments the curing of the soil cement, resulting in an even better end product. Another advantage, particularly when using central plant mix, is that the soil cement arrives at the job site at optimum moisture and proper gradation. It is therefore ready to place and compact, thereby avoiding delays in bringing the material up to optimum moisture or having to dry it out in cases of overwatering or rain. In addition, time-consuming cross-blending with borrow material to achieve proper gradation is averted. A tremendous advantage of soil cement comes from the way the materials are bound tightly together into rigid slabs called plates. These plates spread traffic loads over a large area, greatly reducing subsoil pressures. Conversely, compacted, untreated bases concentrate the load on small areas only. As a result, soil cement helps improve the stability of the subsoil through its bridging effect, while the untreated bases can isolate and exploit weak spots in the subsoil, eventually causing significant shifting in the roadbed, resulting in base failures and potholes. Many materials can be greatly enhanced or transformed into a superior roadway base material through the addition of cement. Lengthier hauls are generally required with the untreated materials. Hauling costs are reduced through the use of the locally available materials in soil cement. Some paving projects will involve new roadbed construction where in-place materials can be used for the soil cement. In those cases, soil materials are already present and available, and hauling costs are reduced even further. The materials in old, unsurfaced roads make excellent soil cement material. Even old bituminous material, once it has become dead and friable, can be pulverized and incorporated into a soil cement base. The opportunity to reuse this material offers an economical solution to control construction costs. Soil cement has been widely used with a great deal of success in many areas of Florida, such as Orange County.
Throughout Orange County, where we have concerns regarding moisture levels or high groundwater tables, in new developments we strongly encourage the developers to utilize a soil cement base. We've experienced that this results in a better product than some of the other materials. Also, on our large road construction projects, we've utilized soil cement as an alternate base material. The results have been almost without exception that soil cement turns out to be the more economical product. We've utilized soil cement in Orange County for probably 20 years and have always had very successful products, and we've been very satisfied with the result utilizing that material.
The use of soil cement is not limited to roadway bases, however. Its stability and erosion-resistant characteristics make it an excellent material for slope stabilization, as shown here at the cooling ponds of this power generation plant near Sanford, Florida. Its low permeability characteristics also make it an excellent material for liners in sanitary and hazardous waste landfills and storage of hazardous materials as well. Whether you apply central plant mixed soil cement or use mixed in place material, the principles of soil cement construction for major highways, roadways, streets, airports, parking, or storage areas are basically the same. Let's review those principles now. The principles cover 3 specific areas. First, preparing the appropriate design mix for soil cement. Second, site preparation. And third, attending to the control factors for construction. The first step is the preparation of a design mix by an approved laboratory. This may be accomplished by one of 2 methods. 1, strength design, or 2, brush loss design criteria. In strength design, 300 pounds per square inch is the most prevalent design strength used. For mixed-in-place processing, a minimum of 5% cement content is also specified by Florida Department of Transportation projects. The second design method is the brush loss method, accomplished in accordance with AASHTO T135. When design is by the brush loss method and processing is done by the central plant method, meeting certain criteria strength testing of field specimens is not required. However, sampling is done at the processing site prior to mixing to assure that the parent soil properties have not changed from those used in the original design. Most roadway applications require a soil cement layer 6 inches thick, compacted to a minimum of 97% of maximum density, as determined by AASHTO T134. For heavier traffic applications, up to 8 inches may be required. The first step in site preparation is to make sure that the proper equipment, material, and labor are available on site to complete the job effectively. Regardless of whether applying central plant mix or mixing the soil cement in place, the process of mixing, spreading, compacting, and finishing the soil cement surface is completed within a timely fashion, so as not to interfere with the cement's hydration process. In central plant mix soil cement, fine grading of the subgrade is performed to assure a proper and uniform thickness of the base. The subgrade is also well compacted to provide a firm, unyielding surface to compact the soil cement base against. This ensures attainment of proper density in the base. Fine grading is a critical element of site preparation for the mixed-in-place method as well. This method results in very little material displacement. Therefore, the shape of the crown and grade at the start of the project will determine what it looks like at completion. Obviously, the composition of the mixture is one of the primary factors in assuring quality construction. It is, however, one of many control factors for construction. Other factors include cement content, moisture content, thorough mixing, adequate compaction, proper curing, joints, traffic. Whenever possible, soil cement is placed in a single layer. Compaction begins immediately after the soil cement has been spread and shaped. Minimum density requirements are about 97% of the maximum density. This is determined by a representative sample taken from the moist mix at the time compaction begins, in accordance with AASHTO T134. Even greater density will be more beneficial. The exact procedures for finishing soil cement depend upon equipment, job conditions, and soil characteristics. Regardless of methods, the fundamentals remain the same. In addition to compaction and optimum moisture, all surface compaction planes are removed. The finished surface should be smooth, dense, and free of ruts, ridges, or construction cracks. The soil cement mixture is then cured, protecting the moisture content of the mixture so hydration can occur. Most soil cement is cured with a coating of bituminous material. Just as with any road construction project, traffic must be detoured from the work area while construction is underway. If the detour cannot be maintained for the 72-hour curing period, light traffic can be routed onto the soil cement base with the approval of the engineer. If the road must carry traffic, the bituminous material can be sanded to prevent pickup. Joints are neatly trimmed with a vertical cut perpendicular to the center line and cleaned of all dry and loose material. Fresh, moist material is then bladed into the joint and compacted. The joint is left slightly high until after final rolling, when it is trimmed to grade. The newly revised FDOT Road and Bridge Specification, Section 270, Soil Cement Base, contains the latest in state-of-the-art soil cement information and is highly endorsed. The Soil Cement Task Force was chaired by Dan Turner, FDOT District 2 Materials Engineer.
First, let me say that the Florida DOT uses a good many different type materials as base course material or subgrade materials. There's no universal base course material. The engineer has available to him a variety of materials that he can place as a base course. There's your aggregate bases, your bound bases, your bituminous mixed bases, straight lime rock bases, and of course your soil cement base. The real trick is using the proper material for the location and the environmental conditions that are prevalent for that particular area. In the case of soil cement, one particular location where it certainly serves for added durability and lack of deterioration is where you're in a wet or a re-wetted area that you know the base course is going to take water intrusion. In a case like that, the soil cement will not degrade. Instead, it'll continue to gain strength. Recently, we rewrote our soil cement specification. It's now labeled as the Florida DOT Specification 270. We've written that specification in such a fashion that it can certainly be applied by the cities, the counties, virtually any municipality that would like to apply that specification. There are some constrictions in it that the counties and the cities need to read prior to applying it, such as having their own quality control plan from the contractor, but they're 100% applicable and no problem to use. Our specification was put together by a committee formed from several DOT engineers and a good many representatives from the private sector, paving contractors. We had guests in from testing labs and appliers or users throughout the state. We hope we've put together something that will marry the industry and be usable by anyone wishing to apply it.
The FDOT specification requires immediate testing for field density as soon as possible after completion of compaction, using the methods prescribed in AASHTO T134, with the required density of at least 97% of the maximum. In addition, for mixed designs accomplished by the strength design method, field strengths of 60% of the design are accepted for quality assurance. No strength tests are taken for mixes designed by the brush loss method. Finishing of all irregularities greater than 1/4 inch must be completed no later than the beginning of the next day using a blade adjusted to the lightest cut, a process normally referred to as hard planing. For local roads and parking lots, 3/8 of an inch is adequate. The removed material is then wasted. Testing for thickness acceptance requires 3-inch minimum diameter holes drilled or dug after hard planing. Thickness is determined by measuring the depth of soil cement in the holes. For mixed designs prepared by the strength design method, field strength testing samples are obtained of mixed soil cement material and formed just prior to compaction. As previously mentioned, field strength testing is not required when the brush loss mixed design method is used, and the processing is done in a central mix plant. Testing procedures are as outlined by FDOT Road and Bridge Specifications Section 270, Soil Cement Base. Important criteria regarding the test specimens are careful preparation and extraction of test specimens from molds, careful handling and curing of specimens. They must be left undisturbed at the job site for at least 24 hours or until they can all be moved without damage, after which time they are carefully collected and transported to a laboratory for curing. There they are kept at the proper temperature and 100% humidity until ready for the 7-day break. Laboratory design strengths are generally higher than results obtained in the field. FDOT has found that for this reason, specimens achieving 60% of the laboratory design strength at 7 days are accepted. The principles discussed so far are basic to all soil cement construction, regardless of whether it is central plant mixed soil cement or mixed in place material. The methods of processing, however, include specific details unique to each. Looking at these details, we will cover central plant processing, mixed in place processing, and recycling failed flexible pavement with cement. First of all, in central plant mixing, the moisture content in the soil material is carefully determined to ascertain the amount of water that must be added. Carefully calibrated equipment is utilized to make sure that the flow of soil material, cement, and water remains constant. The soil is fed from a stockpile into a pulverizer and then into the mixer by a conveyor belt. Cement, which is stored in a silo above the plant, is then placed on top of the material on the conveyor belt or fed directly into the mixer along with the water. The pug mill then mixes all the ingredients into a uniform soil cement mixture, which is then conveyed to a standard dump truck to be hauled to the job site. The trucks are outfitted with protective tarps to reduce the effects of weather while traveling to the job site and to prevent spillage. Central plant mixed soil cement is spread and placed in the same manner as any other base material, that is, front-end loaders and motor graders. It is then shaped and compacted to finished grade. These operations are performed in a timely fashion so as not to interfere with the cement's hydration process. Since the material goes down so quickly, real economy in placement is achieved. The mixed-in-place method mixes the graded and crowned soil material, cement, and water in place with a transverse shaft mixer. Multi-shaft machines can complete the task of mixing the material, cement, and water in a single pass. Multiple passes are performed with single-shaft traveling mixing machines for a thorough mixture. Pre-wetting the soil helps bring the moisture content up to the appropriate level, aids in the pulverization of the soil materials, and saves time during the actual processing. The cement is generally distributed in bulk using a mechanical spreader to obtain a uniform cement spread. The cement is then initially mixed with the soil. A check is made to assure proper mixing depth, taking into consideration the consolidation of the material in the compaction process. Initial compaction immediately follows mixing. After final compaction, the mixed-in-place soil cement is finished and curing begins. Recycling failed flexible pavements with cement is particularly advantageous when base deterioration is also encountered. The only difference between this process and conventional mixed-in-place is that all or part of the asphalt surface material is pulverized and mixed into the base course, depending on the thickness of the asphalt and its brittleness or friability. If traffic conditions warrant and the amount and condition of the asphalt is appropriate, it can be milled off the roadway and utilized for recycling into the wearing surface for the soil cement. On this particular project, however, US 129 in downtown Branford, the Florida Department of Transportation elected to recycle the entire 2.5 to 3-inch thickness of asphalt surface course with cement into the base. The basic intent of recycling with cement is to hold the lime rock itself together when it is subjected to moisture, providing assurance against a repeat base failure.
One of the real beauties of working this through an urban section where we don't want to disrupt the traffic overnight is that if you consider the lime rock without the cement is capable of carrying the truck traffic that might be imposed on it, there's no difference in the construction techniques as far as the first semi can chase the last roller right off of this material and be open as fast as the contractor moves out of your way. Cementation will take place.
Once the old material has been sufficiently pulverized, the area is brought to proper crown and grade. It is now ready for the soil cement processes described earlier. Recycling old road surfacing in a soil cement mixture offers a cost-effective way to replace a deteriorated roadway with one that will increase in strength with time. Not only is this an economical solution, it also eliminates the problem of what to do with worn-out road surface material. Recycling old roads is just one of the ways soil cement saves money and reduces road maintenance. Remember, the advantages of soil cement come from these characteristics. Selective soil material can be of a wide variety of materials. Commercial materials such as lime rock, sand, clay, or shell. Local materials such as in-place qualified soil or borrow, waste materials, or crushed paving materials. The relative composition of different soil cement mixtures is based on the grade and type of materials selected. Variations in soil content and chemistry will affect the amount of cement required. Soil cement is not only strong and highly durable, but economical as well. Whether you apply central plant mixed soil cement or use mixed in-place material, the principles of soil cement construction are proper site preparation, designing an appropriate soil cement mix, and controlling basic construction factors including spreading, compaction, finishing, and curing. Put all these fundamentals together and you have a low-cost paving material that also provides extraordinary strength and support that increases with age. You have soil cement.